Hi, my name is Michael,
No, I'm Marcelo.
and we're going to be going over our design project too. The final application project aims to apply the numerical methods learned throughout the class into an engineering application. The project must consist of two numerical methods that have been developed in class, including an ODE and one other module with numerical methods not used on the first project. These methods must be used to solve problems within the engineering application and promote a solid ground for further exploration. For this project, we're analyzing how a building frame reacts during an earthquake. When the ground shakes, it causes acceleration that moves the base of the structure, which then makes the whole system respond dynamically. Understanding this response is important for designing buildings that can handle seismic events safely. An article written by the American Society of Civil Engineers explains how data has been used for centuries to help engineers predict the severity of events such as earthquakes. As the preservation of human life is one of the biggest engineering rules in the Code of Ethics, the building must adhere to this and therefore must be built to protect humans in the event of a catastrophe. Furthermore, the database used to provide earthquake data was taken from the Peer Ground Motion database. The data provided is extensive and allows precise simulation to be run, which can be incredibly useful when designing structures that are especially prone to earthquakes due to their location.
Our hypothesis was that by using numerical methods like ODE and a second method, we would help simulate the movement of an earthquake while also giving insight into how buildings can be better designed to handle that motion. By applying these methods, we expected to understand how structures respond to and how to improve their ability to resist earthquake damage. To test that, we first used the fourth order Runge-Kutta method. Uh, this is a reliable numerical method that solves the differential equations by breaking them into smaller steps and calculating several slope estimates at each point. It's more accurate than basic methods and works really well for systems that change over time, like a building during an earthquake. For the simulation, we used real ground acceleration data from the 1994 Northridge earthquake, just the first 20 data points. We ran two cases, one with low damping and one with high damping. The results matched what we expected. Lower damping caused more displacement, and higher damping helped reduce it. Even though we only simulated 0.1 seconds, the difference was clear.
So the next method we used was spline interpolation. So why did we use this method? We found that it is extremely versatile in moving between first and second order problems, and with the data found, it fit the trend accurately. Spline interpolation works by building a polynomial function for every interval. Then the first and second derivatives are found to match the start and end segments, which ensure a smooth spline. Finally, the coefficients are solved. The equation used in this method is the quadratic equation, which is ax squared plus bx plus c. The spline method produced a long list of coefficients which could be used to ensure that the spline moved through the data points while showing where the data may move more drastically. Furthermore, a graph was created which represents acceleration seen on the y-axis versus time seen on the x-axis. Although the line moves relatively smoothly throughout the data, there are points where the data may spike. This is likely due to places of maximum acceleration. So in conclusion, the significance of this report is very important regarding safety as well as longevity. Data collection has been used for many, many years to predict how events such as earthquakes may affect the world around us and to what degree. This report was written in hopes of bolstering this fact, as the data inputted and the numerical methods used can help to show at what points of an earthquake may be most harmful to human and structural health.
In the end, the Runge-Kutta method worked really well for this type of problem. It was easy to adjust the values and see how the structure responded. If we had more time, we would expand this to include more data, or even model a more complex building with multiple degrees of freedom. Thank you for listening.